Euler's formula, named after the Swiss mathematician Leonhard Euler, is the formula defined as e raised to the I theta equals cosine theta plus I times sine theta. This formula in particular is specifically established the fundamental relationship between the trigonometric functions and the exponential function, both those functions being complex value functions. It's widely regarded to a lot of mathematicians known as a beautiful map equation. Specifically, if we were to let x, or in this case theta, be equal to pi, it would actually come down as e to the I pi plus 1 equals 0, which in other terms it's also known as Euler's identity, which a lot of mathematicians like to say. For example, like Feynman, he quoted our jewel and the most remarkable equation of all of mathematics. So I'm not really here to give a crash course on or the history on everything on why this formula exists in particular. Mainly, the whole point of this video is just to give you the proof on why this formula exists in particular. But before I start the proof, there's also one thing I want to point out. So we have cosine theta and sine theta. So in other words, we have that cosine theta is actually equal to, in terms of the exponential functions, e to the I theta plus e to negative I theta divided by 2, and then we also have sine theta equal to e to the I theta minus e to the negative I theta divided by 2i. Notice the relationship. We have trig functions on the left, and then on the right the exponential function. So why is this important in particular? Well, this formula actually helps us get these formulas. Now I know before recording this video, I was thinking, should I really get into the discussion of why such formulas exist? And I'm gonna do that, and it'll be quick. I promise. We'll get to the main portion of the video soon. So I'm gonna start with cosine theta equals e to the I theta plus e to the negative I theta divided by 2. Well, first thing I would like to establish is we have Euler's formula for e to the I theta, which is equal to cosine theta plus I sine theta. And then let's consider the negatives. So meeting e to the negative I theta equals, when you plug in negative theta into here, cosine's an even function, so this just stays the same. Wow, when you plug negative theta into sine, that's an odd function, which means it's minus sine theta. So that means we can actually solve this in terms of systems of linear equations, where we can either solve for trig function on one side, and then the exponential functions on the other. So I'm gonna first add these two up. So what this means, this will be I'm gonna put a plus right here, and I'll put a minus just to show the work. So everything plus here. So that means we have e to the oopsies, it's supposed to be. We have e to the I theta, then plus e to the negative I theta, and cosine theta plus cosine theta to cosine theta, and these will cancel out, so we're good. So now we just divide 2 from both sides, and then we actually get cosine theta equals the equation that we want, just like before. Theta divided by 2, like so up here. And then now let's actually subtract the 2. So this means this will be e to the let me get rid of this. Okay, if you subtract these, then you get e to the I theta minus e to the negative I theta equals cosine theta minus cosine theta 0. Subtract these two, you get negative 2. Actually not negative, you get positive. I forgot there's a negative right there. So this will mean we get 2i and then sine of theta. Then just divide 2i to both sides. And then we have what we want. Sine theta equals e to the I theta minus e to the negative I theta divided by 2I, like so. So that's how we get our cosine and sine functions. There's a similar way when you're also finding the formulas for hyperbolic cosine and hyperbolic sine. When you plug in your data for ix, and then the relationship shows, which is very, very similar to how we find our cosine and sine functions. So now you understand why it's important. And another thing we could say is if you set the real part, if you set the real part of the function here, you also get cosine. Set the imaginary part, you get sine. And just like so. Other than that, so we're actually gonna start the proof on Euler's formula and how we derive that. Okay, so what we're gonna do is let's first establish the fact that before I say this, we're actually going to be taking the Taylor series in order to proceed forward with the proof. So what I'm going to state first is e to the z, its Taylor expansion is equal to the sigma from n is equal to 0 to infinity of z to the n divided by n factorial. And so when we plug in our n's, when we get the expansion as 1 plus z plus z squared divided by 2 factorial plus z cubed divided by 3 factorial plus z4 4 factorial plus z5 g6. Oops, that's supposed to be a 6. 6 factorial plus z7 7 factorial plus dot 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 and so on. So this is Taylor expansion for e to the z. So now let's actually plug I theta in substitute for z, and then e to the I theta. You simply just plug I to the theta into all the z's into here, so that we get 1 plus I theta. I mean, I'm gonna write in parentheses, so I theta square divided by 2 factorial plus I theta cube 3 factorial plus I theta 4 factorial. Okay, let me just write this out. 5 6 7. And then when we evaluate this, we get 1 plus I factorial plus, or actually in this case I square is negative, so this will be a minus I, no, not minus I, it's supposed to be just theta squared divided by 2 factorial. Then this will be minus I to the theta cube 3 factorial, I to the 4th, which will be just 1, so it's just theta to the 4 theta, and then minus I to the 5th. Well, actually, to the 5th, this is actually still a plus technically, so 5th factorial, and then this will be negative 1, so okay, it alternates from positive to negative, right? And this will be theta to the 6 factorial plus well, minus still technically I to the 7th 7 factorial plus dot 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 so on. Okay, so now let's actually group these differently such that all our numbers here are with the real parts of the complex number, and then all our i's, which is the imaginary of the Taylor expansion. I didn't mean to say function, I mean to say the expansion. We separate the real part of the expansion and the imaginary part separately. So that's what we're gonna do. And so then we have 1 minus theta square, that, and then plus to the 4th 4 minus theta to the 6 and dot 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 put this in parentheses, then plus I, and then all this be multiplied by data minus data cube, data cube 3 factorial plus data to the 5th 5 factorial, then minus data to the 7th 7 factorial plus dot dot dot. Okay, so this is what we have. So take a closer look and make an observation on these two. So what do you think this could mean? This is, however, this piece, the real part particular, this piece here is actually the Taylor expansion for the function cosine theta equals, and then over here is actually the Taylor expansion of sine theta. So now we can actually come to the conclusion that e to the I theta is equal to cosine theta plus I sine theta. And that's how we get the formula. Pretty interesting formula. I do agree that this function, this formula itself is actually pretty remarkable, especially in complex analysis. Well, obviously it has to be because you have the imaginary unit I. So what else could you use the imaginary number for other than complex? So this formula is very important in, as I said, complex analysis. You could use it in anything like what we did when we find the cosine functions, its trig functions equals to its exponential functions, and it can actually be used in any sort of applications like relating with like topology and other sorts of mathematics, etc. I know topology was the big factor there, the biggest application that I know of at least. So yeah, thank you guys for watching. Feel free to like and comment, subscribe to the video. I also did a video on integrating the another complex value function, 1 divided by a cosine theta with from 0 to pi, or 0 to pi, such that when a is greater than 0. That one's a bit of a toughie, which it also involves with residues as well. And I'm gonna go play Animal Crossing. Yeah, I bought Animal Crossing.